Okay, guys. The plan, if we stick to it today, is to finish this astro stuff, which is thinking about measuring the dark matter masses in different objects, and then tomorrow focus on models of dark matter, sort of early universe physics and signatures. So we talked a lot about, probably a little more than we should have, about the Boltzmann equation. And we looked at one example of this, which was under the assumption of spherical symmetry. What it looks like, and I'll write that down here again. And remember, this is just coming from taking the Boltzmann equation as we had written down, write it down in spherical coordinates r, theta, and phi, and take integrate over velocity. So, for example, you would add VR here and integrate over all of velocity. And in spherical coordinates, that's going to give you this equation that I'm writing down there. And again, it's just a matter of doing it, just a little bit of algebra, but there's nothing particularly subtle about it. Okay. The most important thing here is to know what these different things are. This is the stellar density, or the density of whatever is your tracer particle from which you're trying to measure the potential. So we're just going to think of this as the stellar density, and this is the density in 3D. So as it is in the galaxy, we have pretty much no way of knowing what this is. This is not an observable. This is the dispersion in velocity in VR, which is essentially just the radial velocity. And this R signifies, so let me just draw a picture here. You apply this to a wide range of objects, but one class of objects you would apply this to is satellites of our own galaxy. So imagine you're in the Milky Way here, and there's a satellite galaxy here. We are sitting out here, and we can measure motions of individual stars in that galaxy. Okay, this is if the galaxy, if these small galaxies are close to us, or even as far as Andromeda, a big 10-meter telescope like Keck, you are able to actually measure the velocities of a single star that far away. It's totally incredible. It takes about half a night or so to get maybe a few hundred stars in a galaxy, so it is expensive in that sense, but you can do this, right? And this is why, in the end, dwarf galaxies are going to be such a great way of actually measuring the dark matter. If there are galaxies that are really far away, like elliptical galaxies, those things you can still apply this equation, but it's not the technology is not quite the same thing. Here, you can't resolve individual stars, so what you're doing is you're getting clumps of stars. But you can still get some estimate of the dispersion of the velocity of the stars by doing the same thing. So in the end, the basic equation is going to stay the same. The observations are going to be very different. So this is something that you apply to a really wide class of objects, maybe half of all the objects in the known universe. Okay. So that's why it's important. Now, in reality, spherical symmetry isn't such a great approximation for many cases. So you have to break this. But for us, we'll just start with spherical symmetry, and then and try to see what kind of masses for dark matter we get. Okay, so that's the dispersion in the radial velocity. And when I say radial, what I mean is if you're sitting in the frame of the galaxy, then you define your r, theta, phi coordinates from the center of the galaxy. That's what this is. Okay, so this is in sort of the galaxy or the body frame. This beta is something that we don't know. And this beta is 1 minus. Okay, and so it's basically quantifying for you what sigma theta, which is the dispersion in the theta direction or the phi direction, is. Okay, again, we can't really measure this. All we can measure is what is the velocity along the line of sight. Okay, so this is something that we need to either infer or marginalize over this ignorance somehow. Okay, so this is sigma theta square over sigma phi, and since we've assumed spherical symmetry here, sigma theta and sigma phi will be basically the same. So it's essentially just tangential dispersion versus the radial dispersion. And this d phi dr is the important thing here. So this phi is the total gravitational potential. So it's phi dark matter plus phi stars plus phi whatever else there is, say gas. Everything goes in there. Okay, so even with spherical symmetry, there's no way to actually solve these things analytically for most part, except in a few cases that I'll try to sketch for you, when you can assume that the dark matter dominates everything, and the way you assume it is to do the proper thing and then figure out what happens. Okay, but in the dwarf galaxies, the satellites of the Milky Way, that is the case. Dark matter overwhelms normal matter by factors of at least 10, but more like 100 to 1,000. So it's a very good approximation. So we'll basically look at examples now where phi is essentially phi dark matter. And that makes this more tractable because then the right-hand side is just the dark matter. It doesn't become a nonlinear equation in the stellar density. Okay, so nothing I've written here is an observable. So you have to actually go from something that's observable to this. And what is observable is, like I said, the line of sight velocity of stars and the surface density of star. So what we measure is essentially something like this, which is it's really the line of sight, but for now just assume that line of sight is just z. And basically you're just integrating and getting a column density of stars or whatever your tracer particle is. Okay, and this is something that's observable. You can write this down in terms of an integral over r. Okay, and so this is at some position r in the sky. And we'll use this again. So it's some position r in the sky. What you can measure is the surface density. And you can also measure the dispersion of velocity along the line of sight. So this is just, if I take a bunch of stars at some position r, where r is, we're just looking at it from the center of the galaxy, what is the dispersion in those velocities? And you can write this down in terms of, in the equation, which, so this is just integrating over z, which is r square minus this r square. Yes?
So z is the variable that is from u to the galaxy?
Yes, so z is,
So why is it a negative infinity? Shouldn't it be 0?
it's just you just put the 0 at the galaxy center. But yeah, you could just change variables and say z starts 0 here and goes there. It practically doesn't end up mattering just because it's so far away. That you just. This is the surface density of stars. Okay. So again, this one you can write it out, and I'll just write it down here just for reference. We won't use this now. Sorry, I missed an R here. And I think there's a factor of 2. Again, here we're not doing anything, we're not really doing any dynamics. This is just geometry. So you just ask yourself, If something is moving radially, you're only going to get this component of it. If something has a tangential motion like that, you're only going to get the component along the line of sight. And so when you do those cosines and sines, this is just what it comes out to be. Okay, so this is purely from geometry. So these are the things we have. We can write down the Jeans equation for. These are the things we can measure. Okay, so you got to do this inversion, which adds a little bit of a burden. But we'll make an approximation here, which turns out to be a really good one. And that is that if you look at a whole bunch of these galaxies that are near us, or even some of the elliptical galaxies, and you plot sigma LOS versus R, it tends to be pretty flat, like that. So this is the dispersion. So what we are really doing is looking at a galaxy, go to the center, and then start moving away, and measure the dispersion of the stars. And you find that the dispersion doesn't drop dramatically, doesn't rise dramatically. It's pretty flat. And if it did rise dramatically, that's a signature that it's getting tidally disrupted, perhaps. Okay, so for most of the dwarfs, it's pretty flat at the 10% level, actually. Right? So you can, to zeroth order, you can assume that this is a constant. Again, that'll make what we're going to do now tractable. In which case, this sigma R square is going to be pretty comparable to sigma LOS. Okay, it'll turn out that even that has to be fairly flat in order to give you something that's in sigma LOS that's flat. Okay, so there are some complications depending on what you do with beta, but we're not going to get into that. Okay, so we'll sort of like treat these guys as if there's a one-to-one correspondence, which there is, but if this is flat, this is almost flat also, and then proceed with it, and basically gives you the correct sense of this calculation. Okay, so we need one more ingredient, which is common in pretty much everything you do in terms of inferring dark matter and astro, which is you need to know what functional form to use for this phi dm. You can try to do this non-parametrically, but for us here, it's more useful to do it in some parametrized form. And so we'll do the usual thing, which is assume that the dark matter is cold, and write down this in terms of the expected potential for cold dark matter. Okay. And what we really need is d phi dr in that thing. And remember, that's the definition of the circular speed. So this is just the force, and that's the centripetal acceleration. So it's v squared over r. This vc square is what we can parameterize. So I'll just write this down in a bit of a funny way, but I think it'll make sense once I write it out. For those who haven't seen things in this form, this is the famous Navarro-Franken-White profile. Okay. So instead of writing it in density, I've just written it out in terms of the circular speed. So this thing is just gm over r, where m is the mass enclosed within the 3D radius. Normally, we write this in terms of density and some scale factor, but I've converted it to Vmax. So Vmax is basically the maximum of this function. Okay, so this function attains a maximum when r is equal to 2.16 times rs. So oftentimes people trade rs for this thing r max, which is roughly 2.16 times rs. And again, if you plug this function vc attains a maximum at R max. Okay, so you can either think of it in terms of RS or R max. Doesn't really matter. But there's some parameter that sets the overall density normalization, and there's some parameter that sets the length scale normalization. So this is sort of the size of the halo, and that's how massive the halo is. Okay, and if you want to convert this to a density profile, I'll write that down here. The Navarro-Franken-White density profile in terms of those things I gave you there, can be written in the following way. So this is just putting in all the numbers. It's a very convenient way of dealing with. So for those who have looked at this before, you now see the usual NFW density profile down here. At small radii, it diverges as 1 over r. At large radii, it falls off as 1 over r cubed. All I've done here is now to you put the normalizations in terms of this Vmax and Rs, okay, which is going to be crucial for us, and then put everything in these solar masses per kpc cube. As a quick check, you can put in something like Vmax equals 160 kilometers per second, and I'll tell you why 160 in just a sec. I don't know if I wrote this down. I hope I did. Rs of something like 30 kpc. Plug it in here and ask yourself, what is the density at 8.5 kpc? And you'll find that this is very close to 0.3 GeV per centimeter cube. Or it's more like 0.3 or 0.4. So this is the typical halo of the Milky Way. We'll have a Vmax of 160. Why is it 160, not 200, which is what we measure? It's that because the baryons are important. The rest of the stuff comes from the disk. And you take this and you add the baryons on top of it, you're going to get something like 200 kilometers per second or 220. Okay, so this is a typical Milky Way halo. It has a mass of about 10 to the 12 solar masses. You can use this to like figure that out. No, baryons just add. So remember, you have to. Right. So you got to add in quadrature essentially. That the contribution that comes from the disk and this and that. In the local neighborhood, they're roughly order unity. They're both roughly equal. Okay. So the only number I haven't motivated really is this Rs of 30 kpc, which is the last thing we need to actually do this calculation. Okay, but is this clear? This is why I said in the sorry, go on.
Sorry, what is Vmax? What is that number?
That's basically if you look at Gm over R, we're just parametrizing the maximum value of that in terms of Vmax. So it just gives you
like what is the maximum value of that? Like if you look at a galaxy, it has a spread and distribution. What is Vmax?
So if it was, we'll see how Vmax is related to like this sigma LOS in just a second. But if you had a spiral galaxy that was rotating, then Vmax is essentially going to be the maximum velocity you measure.
Like the velocity of stars that are farthest out.
Yes, as you go far out, you typically see a rotation curve. If it's a rotating galaxy, if it's a angular momentum supported galaxy, you see the circular velocity curve rise, and then typically it flattens. So that flat part will be pretty close to Vmax modulo whatever the baryons contribute. Right? So that's why it's a nice number, because you see a galaxy and somebody tells you, okay, it has a flat part of rotation curve of 100 kilometers per second. Then Vmax is close to 100. It's not going to be 200. It's not going to be 10. Right? It's going to be within 20, 30% is going to be close to that. So that's why it's a nice way of parameterizing things.
And how did you actually get that 4.625?
That's just to make sure that when you put in this into R, you actually get VC equals Vmax.
I see.
Just that function is 1 over 4.625 at this value. Right? You just take the derivative of that and you find that it's 0 at this value. So it just becomes a maximum.
So it's not a function which you made up?
No, this is not. This is what, okay, so this is an excellent point. This is what comes out of numerical simulation. So for about 20 years, when people have run numerical simulations with collisionless dark matter, basically the average profile of the dark matter looks like this as you go, and that's basically the same as this one. Okay, so it's
well, that's completely simulation.
This is from simulation, so yes. And it looks like it's a 2-parameter model, but in fact, except for some little bit of a spread, it actually is a 1-parameter model because there is a relation between Vmax and Rmax. You're not allowed to like vary them freely. That relation depends on cosmology. So for the, let me write it on up there. So for the simulations that were run at Santa Cruz, this Bolshoi simulation, I'll just write them down. It doesn't, the flavor of it doesn't change too much, but this is a pretty reasonable. So I think it's sort of the WMAP 7 cosmology. So as I said, most people will write it in terms of Rmax. And this is okay. So what this tells you is that if you look at a halo which has a maximum velocity of 100 kilometers per second, then the Rmax for that halo is about 30 kpc. Okay, so that gives you an idea of the sort of the extent of the halo. The halo goes out much further than that. This is where this rotation curve peaks, but it keeps going on. But it gives you a good sense for like, you know, what the size of the halo is. I mean, in this case, the halo will probably go out to about 150 kiloparsecs. But that's the scaling. So there's scatter in this, and scatter is about 0.15 dex, and you remember dex is 10 raised to something. So a scatter of 0.3 dex is about a factor of 2. So it's less than a factor of 2 scatter between this Vmax and Rmax. It's a beautiful relation. It goes from the smallest galaxy halos you measure to the biggest clusters. It comes out as this power law, 1.28. Again, that's for this particular simulation. That number will change a little bit, but it's close to 1.3. Okay. So this immediately also tells you something else, which is that this Vmax is directly related to the mass of the halo. Remember, there's only 2 parameters in this. So the mass of the halo just dimensionally has to go as Vmax squared times Rmax. And the way you see that is Vmax squared is Gm over R. You multiply by R, you have to get back something which is mass. So this has to go like this. There's only 2 parameters in this. And Rmax goes as 1.28. Let's just approximate it as 1.3. So the mass of the halo goes as Vmax to the 1.3. So as soon as someone tells you Vmax, they've also told you roughly what M halo is, which is why this is such a nice formalism. And if you want to normalize this, just remember that Vmax of 160 kilometers per second gives you a Milky Way, which is 10 to the 12 solar masses, and then you can scale from there. Okay, does that make sense? Yeah. So if you wanted to write this number down, you would, and this one is not exact, but I'm just writing down something which is roughly true. 10 to the 12 solar masses for Vmax for about a 160 kilometers per second raised to 3.3 power. So again, that's the sense in which I said Vmax gives you the size of the halo. So it's a very well-defined theory now, and that's what comes out of collisionless dark matter. And so we can test it, okay, up to some scatter. Any questions about this? Does it make sense? There's the slight complication here is that all of this I was thinking of galaxies out in the field. When galaxies fall into other galaxies like satellites, then this relation gets modified a little bit. Okay, but it's a small crinkle. I'll tell you about it just when we need it. Okay, so let's just apply this now. Okay, so let's go back and solve this equation. So we are looking at that the Boltzmann equation there. Sorry, the Jeans equation. This is called the Jeans equation after the guide. Okay. Let's do the approximation where beta is constant. Okay. So otherwise the solution looks a little more complicated, and it's really not worth going through it right now. If you make the approximation that beta is constant, then you can just integrate that equation, and you will get okay, so that's just the solution of that that differential equation with beta being constant. And the reason why you have a VC square coming from there is just the d phi dr term. D phi dr is VC squared over r, and so that's where when you just solve the equation, because there's a 2 beta there, that's what you need to solve that differential equation. Okay, so that's just that equation integrated out. And if beta is 0, you can just see that you can just forget about this term, and that's just an integral over the last term. VC squared over r is just gm over r squared. Okay, so VC squared over r is just the acceleration. So let's look at VC squared over r. No, this is integrated over in there. Okay. So this VC squared over r, I wrote down the functional form for that here. So if I go to very small radii, you can expand out this log. The first order term will cancel r over rs, and the numerator will give you something which is r squared. So r squared divided by r is going to be r. And so at for r much less than rs, and we'll motivate this in just a second, this is going to be a constant. Okay, and that's just the statement that the acceleration in the inner parts of NFW halo or cold dark matter halo is constant. Okay, so you have a constant force. Makes sense? So that makes our life very easy, actually, in terms of this solving this. We don't have to sit around and integrate this. You can sort of see that basically, since this is roughly constant, sigma squared over r is just going to be given by this VC squared, whatever it is, over the at the radii where rho star has support. Okay, and this rho star is the stellar density profile, and there's various forms. But one, if you want to play with something, one form to use, which actually fits most of the dwarf galaxies pretty well, is something like this. This has a name. It's called the Plumber Profile. The motivations for this is not don't worry about it so much. Just the thing to remember is that RP says the size of the stellar disk, or in this case the spheroidal distribution of the stars, and half of the light is going to be within a radius that's 4/3 of this RP. Okay, so RP essentially tells you something about where most of the stars are. So if I say RP is 300 parsecs, then it basically tells you that half of the light in that galaxy that you see is within 400 parsec. Okay, so this is a directly observable thing. Okay. So this functional form for rho star, again, you really see sigma star, but under the assumption it's spherically symmetric, you can deproject it and get rho star. That is, something that we know pretty well, so you can put that in. The main thing here is that this RP for dwarf galaxies is much, much less than RS. RS will be something like 4 or 5 kiloparsecs for the NFW halo, whereas the stars are distributed over a few hundred parsec to a kiloparsec. So this is typically much smaller than RS, which means that this approximation works, which means that the acceleration is roughly constant. And so then you can convince yourself with a couple of lines that this sigma r squared will turn out to be some number here that I'm not going to put. It's an order 1 number. Okay, and the form for this just comes from the fact that we're sort of integrating over a range which is RP, where the stars are, and Vmax squared over Rmax squared. That's basically the scale for the acceleration in the halo. Okay, so that's essentially it. Depending on what you assume for beta or the profile, this number will change, but it's always going to be order unity when you do this, simply because of this scaling here. Okay, and so now we've directly related something that's very close to an observable for a dwarf galaxy to a prediction of cold dark matter theory, which is this. That's an observable, and that one is more or less an observable because remember that this was flat, and if this is flat, these two guys have sort of a one-to-one correspondence. Okay, so let's put in some numbers, and we'll leave this as order unity, but remember that there is a factor there. So let's take an example of a galaxy like it's Fornax. This is the biggest satellite, dwarf spheroidal satellite we have in the Milky Way. There are bigger satellites, the Magellanic Clouds, but they have rotation and they're much bigger objects. This is what you would call a dwarf spheroidal galaxy, right? So all of the Fermi constraints, for example, on annihilation rates, they are dependent on these dwarf spheroidal galaxies. So Fornax has a sigma LOS. It's a little more than 10, but I'm just going to round it up and use 10 for now. You'll see why in just a second. It's the most extended. So its RP is something like a kiloparsec. So let's, we have this, that, plug that in, and you get Vmax squared over Rmax. Okay. Again, so it's 2 parameters, but now remember that there is a relation between them. Okay. And so you can take this and plug it in there. However, you have to be a little careful because these guys are satellites of the Milky Way, right? So you don't want to use exactly the same relation. When something falls into the Milky Way, it gets truncated. And the relation changes a little bit. So I'll give you another one that you can use for the satellites, if I have it written down here. So for subhalos, which are halos within bigger galaxies, the relation looks something like this. And this is from the latest simulations that people have done at Irvine, looking at these kinds of systems that are like the Milky Way and Andromeda. And you get something like this. And you can see that the power is a little different, but the normalizations are about the same. So it actually wouldn't have made too much of a difference if you had used the other relation. But you can go ahead and use this now. And at this point, you basically have, so just go ahead and plug this in. And you will get an estimate for Vmax. And you will end up getting Vmax is 5 kilometers per second. Okay, which is kind of bizarre because the stars are 10 kilometers per second, right? Thinking about the dark matter sitting in a potential, well, that's 5 kilometers per second. It's a little weird. Okay, so it seems really bad. However, you got to remember that there's a spread. So if you plot R max versus V max, they look like that, but they're scattered around this. So if you allow for the scatter, this can go up. You can push it up to like 15 kilometers per second or so, okay, with scatter. But then you pause and you ask, why is the biggest dwarf spheroidal galaxy in the Milky Way sitting in a 15 kilometer per second halo when the Milky Way should have enough 40 kilometer per second halos floating around? Okay. Why is this sitting in such a low density halo? Another way of thinking about this is if I plot number of halos, greater than some Vmax versus Vmax, they'll look like that. If you go to like 5 or 10 kilometers per second, there's a huge number of them around in the Milky Way. It's like maybe, few hundreds. I don't remember the number exactly. It could be 1,000, right? But there's one Fornax. It's one of the most massive. It is the most massive dwarf spheroidal galaxy. It should really have been sitting in, instead of sitting in 10, it should have been sitting in a 30 or 40 kilometer per second halo here.
Why is 30 or 40 the magical number?
Excellent. Why is 30 or 40 the magical number? Because if you take the Milky Way halo is about 160, and so if you look at the things that fall into it, then they're less massive. And roughly speaking, around 40, 50 is the biggest subhalo that you get. So that's where it comes from. Yeah, it comes from the fact that we know we're sitting in a Milky Way size halo. Okay, so I can't go into this in more detail, but this is essentially something now called the too big to fail problem, which is that galaxies we see tend to want to live in halos that are less massive than you would expect. And it's not just the Milky Way or Andromeda or things around us. It's basically out in the local volume, wherever we can measure it, this problem seems to be there, which is that small galaxies seem to want to live in halos that are less massive than you would expect. Yeah. So I did have a simple setup to do the tidal calculation. You can convince yourself that if there is any dark matter in these guys, then it's very hard for the tides to affect them, right? So your choices either are don't have any dark matter, and then you have to somehow explain why they have a flat dispersion, why they're even together, or if they have dark matter, then they're not really affected by tides so much. The small guys, some of them will be. I mean, there is a too big to fail in the field, and there's a too big to fail in the Milky Way. I mean, if this problem was just for the Milky Way, I wouldn't really take it that seriously because Milky Way is one object, and you can come up with all sorts of ways around it. But it's very pervasive. It's out, it's in the local volume everywhere, right? So that is something. There's something systematic going on. Now, it's not that every object is like this. I'll give you another example, which is not like this, which is Draco. It's about a couple of orders of magnitude less luminous than Fornax. Its sigma LOS is also, in the approximations we are doing, 10 kilometers per second, but its half-light radius is more like 300 parsecs. If you go through the same calculation, you will find that Vmax of 30 kilometers per second is totally fine. Okay, so Draco can live here. Okay, so you can put Draco here. And you're going to put Fornax, which is more massive in stars, somewhere here. And the problem really isn't that you can't find one of these objects to sit in something that big. The problem is there's too many of these big subhalos, and most of the Milky Way satellites want to be on this side rather than on that side. It would have just have been nicer if they all wanted to live there. Then there wouldn't have been a problem.
It's also amazing
So the missing satellite problem is on this side, which is that if I just extrapolate this curve to very small Vmaxes, there's a whole bunch of them, not just thousands, hundreds of thousands, right? Depending on how far it's down. And the question is, where are they? This one's more of the massive end. We are basically saying that the observed satellites are not living in dense enough halos. Essentially, that's what this problem is saying. Right? So one way around this is to like somehow make the halos less dense. Okay, either by feedback or through dark matter physics. Then this formula no longer applies. You may have some Vmax, but as you go in, you can't use this because this was for cold dark matter with no feedback. So feedback can change the functional form of this and get you back something that might be consistent. Again, that hasn't, that's not easy to do, neither in like models of dark matter nor with feedback for these satellites. So there is no, I don't think there's a good solution to this yet. It depends on how you look at it, right? I mean, the missing satellite problem, you might say is not so much of a problem because if I go to very, very small halos, then I don't expect them to hold on to their gas and form stars. And so maybe that's why you don't see them. I'm not saying that's a completely solved problem either, but I'm just saying like it's a different flavor of a problem. Yeah.
It seems like there has been a couple of empirical formulas comes in to express the final Vmax.
Yes. So, which you're talking about the Rmax Vmax relation?
For example, this so NFW or Plumber or the relation R and Vmax.
This thing is from simulation, so that's your theory.
Yeah, so that's what I call it.
That's not empirical, that's theory. Okay, anyway.
Or what about the Plumber formula?
Oh, the Plumber, that is actually measured. It doesn't matter what form. I just gave you, if you ever wanted to do a calculation, use that. But this one is not important. The only thing that's important is this density profile here for the stars falls pretty rapidly. And it falls over a scale RP that's much smaller than RS.
So you are saying, for example, final Vmax will be
to the yeah, as long as it falls off pretty fast, which the stars do when you look at them, right? So this is observed, right? Yeah, exactly. So yeah, this you have to put in the observations to get out this statement, but and, this is a little hand wavy, but this is the only way I could do it to show you, sort of without in a simple way that how the Vmax is related to something you measure. But when you do it properly, this is the end result that comes out. Okay, so one of the things that's this formalism, having to go through all of this, you still end up with issues with like this beta. Note that I sort of like didn't talk about it, but if you allow beta to vary, then it becomes a little more difficult to do this. And yet, at the end of the day, you get back the same result. And so it turns out that this whole exercise of taking spectra of a whole bunch of stars, doing this inversion, applying the Geodesic equation, all of that really ends up giving you just one data point per galaxy. And you can sort of show that almost as a proof. And so let me just give you, in the end, an even simpler way of doing all of this, which is the following. So take spectra of stars, get velocities, apply Geodesic equation, do everything else, and then after all that effort, this is what you get. The total mass within the half-light radius of stars. So this is something we observe, right? This is related to RP. Is basically 700 times sigma LOS square in kilometers per second square times R half of the stars in parsec, and this is 700 solar masses. Okay, the proof is long and involved, but this is kind of like the virial theorem we almost said, we talked about, but it's not. Yes, go on. Good question. I mean, so I don't know where did I draw the. Yeah, right here. And the missing satellite's sort of out here. Like I said, it's a different flavor of a problem. It's basically asking this question that in WIMP scenarios, actually in most scenarios, and we'll talk about it on Friday in terms of like what sets the minimum mass of the halos here. But in most of the models of dark matter you write down, you expect to see small guys floating around, right? Like we should be like in our own galaxy, there may be like billions of these small guys floating around, right? And so the missing satellite problem is really a visceral problem of in a way of saying, how do we see that? It's a key prediction of cold dark matter. Where are these guys, right? Why don't they light up, right? And so the way around that could just be that you don't see these small guys because they haven't managed to form stars. They're just not big enough to retain the gas, right? And there's this one way around it is basically that when reionization happens, there's a lot of UV radiation from the first stars at Z of 6 or 7 or 8, and that can knock the gas out. So if your dark matter potential is not big enough, so if you're at 5 kilometers per second and the gas gets a kick of 10 kilometers per second, it's gone. You don't retain it. If you don't have gas, nothing cools, you don't form stars. So that may be a way to solve this. In detail, whether it does or not is still under debate. But this problem, the too big to fail, which is at this mass event, is really saying something about, you can think of it in terms of numbers, but it really is saying something about the density of the halos. It's saying that the observed systems tend to want to live in less dense halos compared to the dark matter only simulations. And that's the same sense in which the cusp core problem is. Because you make a core, you're lowering the density. So this is definitely related to the cusp core problem. But it's talking about it in a way where you're not saying anything about the profile. You're just talking about how much mass do I measure, and is that commensurate with what I expect? Another way of phrasing your question is, if I just make a core in this galaxy by fiat, let's say you just do it by feedback or by self-interacting dark matter or something like that, will that push it up to 40? And it's not clear. I don't think it does. So I think this is still an open question. There's no good answer for it. Yeah. Oh, yeah, actually, this is good. This was Mike Bohlen-Kolchen's, he came up with this after seeing an HBO show about the banks failing. So what is failing here is that these 40 kilometer per second halos, they're so massive that as you track them back in history, most of them stay massive enough that they should retain the gas. Right? Whatever else, all the junk that's going on, all the UV radiation that they're being bombarded with, that shouldn't get rid of their gas. So you would imagine that these satellites are too big to fail to form stars. And so that's where the title comes from, is, are they too big to fail? I mean, and normally if you just look at a cold dark matter theory, they should have formed stars. There's no reason for them to not have formed stars. Right? So there's a distinction between something below around 10 kilometers per second and something above 10. Below 10, most people will say there's no guarantee these guys are going to form stars. 10 to 20, not so clear. About 20, 25, they should form stars. Their potential, well, it should be deep enough to retain the gas and form stars. So, some of them, they are spread out over here. The main issue just is that there's a lot of halos at 30 to 40 kilometers per second. Why don't we see them? Right? And it could be just that your theory is wrong, or or remember, this is from simulations that don't include baryons. It could be that you're not putting in the baryons correctly. There's all kinds of possibilities, but it is a problem. Okay, so although this was, I did this for these dwarf galaxies. You can apply this machinery to pretty much anything as long as it's not rotating. And this formula is a good one to have. It's so simple that as soon as someone tells you the dispersion of stars in a galaxy and how spread out the galaxy is, you know how much mass there is. Okay, so for example, you can do this for Draco or Fornax, and you will find. So let's do this for Draco. And remember, I said sigma LOS was around 10 kilometers per second. R half, let's take 300 parsec. That's the extent of Draco. Plug it in, and you'll find this M, R half, is about 2 times 10 to the 7th solar masses. Okay, so what this means is the total mass of everything within a radius where half the stars are. So this is a radius you can measure. Everything here is measured. This is measured, that's measured, that's the same as that. Right? So the total mass, doesn't matter what it is, stars, gas, dark matter, everything. If you plug these numbers in, you get 2 times 10 to the 7. Okay? And Draco is a dinky galaxy. It's about 10 to the 5 in stars. So this is at least about 100 times I think it's 10 to the 5. So it's about 100 times more dark matter than stars in Draco. Right? I mean, this is the best, for me, evidence of dark matter existing, these dwarf galaxies. You just measure the dispersion and you get the mass. You don't have to do much. Okay. So as a particle physicist, if you don't care about all of that stuff that's gone in, that's a formula you can just use for any of these galaxies. Okay. It works very well for any dispersion-supported galaxy. And even though it's sort of been derived under the assumption of spherical symmetry, people have done this for like axisymmetric systems, and it turns out to actually work pretty well even there. Okay, so it's a very good first-order approximation. Okay, so I was going to do the local measurements, but we're sort of running low on time, and then I don't want to be doing this tomorrow. We want to sort of try to summarize and think about models. So I think maybe what I'll do is give you another way of measuring dark matter, which we haven't talked about, which is gravitational lensing. Okay, so the local measurements that I didn't talk about is basically the Jeans equation, but you can't use that anymore. You need to actually use an axisymmetric system, because remember, the disk is not spherical locally. So it's a different equation, but the philosophy is basically the same. It's measuring dispersions of stars locally and trying to infer how much mass there is. Okay, I will put it in the notes if you want to look at it later when it's out. You can do it in sort of this hand wavy way to figure out why you get 0.3 GeV per centimeter cube. But I'll maybe give you a new technique, which is lensing. Okay, so this is all using stars or some tracers to measure the amount of dark matter. The other common technique that we use to measure masses of galaxies, and in fact this is the way forward in cosmology also, is lensing, is gravitational lensing. So I'll start. So we need to set up an equation that tells you how photons get lensed. Once we have some idea of this lensing, we can backtrack and try to figure out like how much mass there is in the thing that's doing the lensing. The easiest way to do this and to make this make connection to what Scott was talking about yesterday, I guess yesterday or day before, is tomorrow. No, I think you already talked about this. This is the geodesic deviation. So you start with the action, but he'll talk more about lensing tomorrow. I guess that's what he's saying. Yeah. And he briefly mentioned this, that you can vary this action with respect to the coordinates, and you're going to get the geodesic equation. And I'll write them down here. And by now, you guys are all experts at looking at Christoffel symbol and figuring out which one's 0 and which one is not. But that's the vary this action with respect to the coordinate, and then that's the geodesic equation you get that tells you how a photon travels. All the metric and everything goes in here. The metric that you've seen before, and again, if you want to go through the derivations of this, you can look at the step-by-step notes in Scott's book. But here, let me just write down the metric we're going to use, which I didn't actually write down here, but I think I have the right signature. Okay, so phi and psi are the two gravitational potentials, and you've seen this in the CMB lectures. It's the same thing. All we're really doing now is looking at the path of the photons. So take this, dump it in here, a little bit of algebra, and you will get out the path that the photons take. Okay, so I'm going to skip about 2 pages of algebra here to get to the equation that we need, which is an equation that tells you something about so let's define this. This is the measured position of the photon on the sky. Okay, and this is where you think the source is. Okay, I'll draw a picture in just a second. And this is related to the potential. That's doing the lensing. Okay, so as it stands now, what I'm going to write down, the form of it may be not something that I can intuit, but it shouldn't be that surprising that it's something that depends on the potential. Let's see, how do I want to write this down? Okay, so let me write it down in a more simple way first. Okay, so this is a gradient on the sky. Theta is the angles you're measuring on the sky. So just think of it as like x and y. Okay. On the sky, that's the only information you have. And this phi is not actually either of these two things, but this phi is basically something that's integrated with some window function over the actual potentials. So I'll write it down in just a bit. Okay. So what this tells you is that the position you measure for a photon is different from what it started out as, and the difference is given by this gradient mapping, where phi is essentially the integrated potential along the line of sight. And so everything along the line of sight that gives you a gravitational potential is going to contribute to lensing. Okay? So in reality, if a photon started out there, it can get like kicked like that and get to you, and you might think you would measure its position by drawing a line there, and you will think it came from there, whereas it really came from there. Okay, in weak lensing, there's no way of actually figuring this out exactly where it came from, where you can statistically do things. With strong lensing, something I'm going to explain in just a second, you can actually do this. You can invert this and actually get the source position, and you can get the potential. Yes?
So if the gravity is the source and the how do I know the amount of error I make compared to the smaller than that?
So you can explicitly check the second order effects for weak lensing, that they are actually small. The other way to think about this is these, even though when you get nonlinear, these potentials themselves are pretty small, because potentials tend to be of order GM over R, and that's much smaller than C squared. But you can check the second order effects and check that they're small. For the things I'm going to talk about now, I guess Scott's going to talk about weak lensing, but I wanted to talk about a scenario here where you actually get multiple images. Okay, so imagine that there's some here's a source sitting out here, and here's us. Right? And as this, if there was nothing, then light from this source would come directly to us. But because of this massive object sitting in the middle, essentially you're going to get something like, now in reality it's not that sharp, but if this is traveling gigaparsecs, and the size of your galaxy or cluster is a megaparsec, essentially you can make this approximation that most of this bending is happening in a very thin plane. Does that make sense? Right? So this is sort of assuming that the lens is very thin, and most of the lensing is happening just at this one position. Okay. And it turns out that when you do that, this phi is really just an integrated gravitational potential contributed by this galaxy. No, it doesn't have to be a disk. I mean, I can put let me just put a perfectly spherical thing here. All I mean is this distance here is gigaparsecs, and this thing here, it's not drawn to scale obviously, is megaparsec. So it's just much smaller than the path length. Right? So you can do the usual Born approximation for this thing and compute the potential along the unperturbed path. These perturbations, these angles are very small. These differences tend to be anywhere from, so on galaxy scales, theta minus beta is of order arc seconds, or tens of arc seconds. Okay, and when you get up to clusters, theta minus beta gets up to maybe as much as an arc minute. Okay, this is sort of the upper end of it. Okay, and these are things we can measure. Remember that if from the Earth, the best telescopes have resolutions of a quarter arc second or so. With adaptive optics, even a tenth of an arc second. Hubble Space Telescope has a resolution of about tenth of an arc second. So you can actually measure these splittings if the guys doing the lensing are galaxies or more massive objects. Okay, let's see. So let's take one example, and in order to make this somewhat quick, we'll, instead of dealing with an extended galaxy, I'm just going to imagine that there's a point source there. In detail, you'll change things by factors of 2 if you assume an extended galaxy. But you could just imagine that this whole thing is concentrated into a very small region and do the lensing. Okay. Excellent. Yeah. So So give me one more line, and then we'll define that. Okay. So we dropped this. We wrote down that gradient map. I didn't quite define that phi exactly, but it is something that's integrated over the gravitational potential of the galaxy. And the gravitational potential of the galaxy, for example, if it's NFW or anything else, you know how to write that down. Okay. So let me define something that's important in lensing, which is the magnification. Okay, and so typically when we are doing, if you have a lens and you're doing a lensing, you look at the size of the image versus the size of the object, and that tells you how magnified it is. It's exactly the same thing here. We can look at this is sort of a clunky nomenclature, but this is a matrix. Beta has two components, x, it's x and y. And theta has two components, x and y. And so let me just write it like this. Okay. And so this is source over position over the image position. For the magnification, you want image over the source. And so you just take this matrix and you invert it. And you find its determinant. And that tells you how magnified or demagnified some images. Okay, this sort of makes sense. This is what you can get out of that. And the reason I wrote it this way is because from the equation above, you can write beta is equal to theta minus gradient of phi. Right, and so then I can take this derivative, kind of easily, because beta I is just theta I minus this, and so the components for that would be right? And again, phi is something that you set up. It's a potential that you're going to set up, and left hand side theta is what you measure, and you try to infer phi. Before we were trying to infer phi from motions of stars. Now you're going to infer phi from looking at lensing. Okay. So this quantity, this magnification, can be written out this way. Let's see if I can do this quickly for a point lens. So when you look at this, you will find that there are certain places for which mu of theta formally becomes infinite. Okay. So basically, there are source positions where if you put a source, then formally the magnification becomes infinite. I mean, in reality, everything has a spread, and so this doesn't really happen. But these, the places where mu of theta goes to infinity, or this determinant without the inverse goes to 0, are the places where you get huge magnifications. Okay, and that's relevant to this weak lensing versus strong lensing. It's the size of the source. So you can show that because it's a gradient map, the surface brightness of the object doesn't change. So when something gets magnified, all that means is you're just getting bigger on the sky. Yes, that's exactly right. So the source size gets bigger, but you're just getting more photons. It's essentially photons that somebody else is not getting because it's been bent to you. Okay. Yeah, I wish we had a little bit more time to sketch this out. But these curves where mu of theta goes to infinity are called critical curves. And so for a galaxy like this, let's say that's the center of the galaxy, a critical curve might look like that. Okay. If you're basically your source is somewhere out here, okay, then typically you're not going to get multiple images. You're just going to get some bending like this. Okay. And in weak lensing, what tends to happen is if you start out with something that's spherical, when you look at it, it starts looking elliptical. And that's the signature that we're trying to measure, and I guess that's Scott will talk about that. But if some source is closer in, as you move across a critical curve, for potentials that are non-singular, you will form 2 extra images. So instead of having just 1 image, you'll start having 3 images. Okay. And now in reality, one of those images ends up being right in the middle and pretty much unobservable. So you typically only see 2, but now you start seeing doubles, right? The same guy has 2 images. And looking at those positions of those images, which is this, and putting in some functional form for phi, you can solve this equation. And you can infer the parameters of the phi, and you can ask how much mass do you need to explain this lensing. Strong lensing means you just see multiple images, and that's basically it. And you need to go over a certain critical density to do that. Okay, so so we do this, basically this multiple images forms in a variety of environments. So let me just give you some examples of things. So let's take an example which is a point lens. Okay, so imagine that there's a huge massive black hole sitting there. It doesn't quite matter, you can take something extended also. And let's take a source, which I'll denote by a cross, somewhere there. Okay, and then ask yourself where the images form. And actually, it's fairly simple to do that using that equation. And what will happen in this case is, let me just draw that critical curve here again. So here's the center of the source. And to make it interesting, let's make this into a circle. Then what will happen is there'll be one image that forms here, and it'll look like this. And another image will form here. They're distorted. Their size is bigger. They're magnified. And in this case, you're getting 2 images of the same object. Okay. This distance between the images, or this sort of this typical distance at which images form, is called the Einstein radius. Right? And just like sigma LOS is a measure of the dark matter mass, this Einstein radius is a quick way of like inferring how much mass there is in a system. So you will forgive me, I didn't derive this for you, but I'm just going to give you a simple number that you can use to just guesstimate the mass. Okay, and what this formula is saying is, if you have something at some distance d, so the lens is, let's say, at a distance d, which you measure in gigaparsecs, which is the typical cosmological distances if you have objects at redshifts of, let's say, 0.5 to 1, and you measure splittings of order 1 arc second, then the mass that's doing this lensing is about 10 to the 11 solar masses. So this is the sense in which I said if you have galaxy scale lenses, you get arc second splittings. Put in a cluster, which is 10 to the 15 here, so that this would be 10 to the 4. Square root is 100. You would get 100 arc seconds, which is about an arc minute. Right? So a cluster of galaxies is so humongous that it's going to make multiple images that are essentially spread apart by about an arc minute, which is a huge angle when you're looking, trying to measure something. It's very easy to pick out. D is the typical distance to the lens and the source. It's the lensing distance. So if it's at cosmological distances. So we'll end this by doing one quick thing, and then which is I said Einstein Ring. So you can ask yourself how this becomes a ring. And that's, again, pretty simple to do from that equation above. Push this source closer and closer to the center. Okay, so let me put this source right here. As you push this source closer and closer to the center, this image is going to move in like that, and this image is going to move out. And as you move closer and closer here, you see that these images are moving towards this critical curve. And critical curve is the place where the magnification becomes huge. And so as I move this in, what's going to happen is you're going to get images like this. Now it makes sense? And as it goes right on top of the center, these guys are going to merge, and you're going to get the Einstein ring, right? So Einstein rings are very special things where the source has to be aligned with you and the center of whatever is doing the lensing. It's rare, but it happens. And when it does, basically a galaxy will get turned into a ring. But most of the time this doesn't happen. You're off center, and so you get multiple images. And the reason I was doing everything along this axis is because if I'm assuming spherical symmetry, then this is the only axis along which anything can happen. Right? So you can see a whole host of these kinds of strong lensing systems. I don't remember how many there are. Might be close to 50 or 100, where you can see these splittings from galaxy scales to cluster scales. And you can estimate the mass. This theta E is supposed to be the Einstein ring, but it basically gives you this, essentially it's the splitting between the images also to order 1. So if you see 2 images in an object in any paper doing strong lensing, figure out what that splitting is. They give it to you in arc seconds typically. You can immediately guess what the mass is that's doing the lensing. And in a cluster, if you're estimating it's 10 to the 15 solar masses, there's not enough baryons to do the job, right? So this is another great way of telling how much dark matter there is in a system. Okay. Yes, so this is essentially this theta E. Square root of the mass of the object that's doing the lensing divided by d. Okay. D is the to determine d, you need to know where the lens is and where the source is, and what the redshifts of those things are. And so typically the way you would do that is you get spectra for these, and so you can figure out the redshifts for these things. So then you would know d from that. Okay. Okay. So we are done with on Friday. We'll not go back to the mass measurements. We'll go to CMB and early universe and talk more about just dark matter models. Okay. Thanks.